Many a times in real life we come across events which has only two outcomes that matter. Either you pass a test or you don't. Your flight is on time or it is delayed. In probability, such events are referred to as Bernoulli trial. Today's lesson will focus on Bernoulli trials and the corresponding binomial distribution. So, what exactly do we mean by Bernoulli's trial? Bernoulli trials are special trials which were a term which were founded after the Swiss mathematician Jacob Bernoulli. And what do they mean? They say that trials of a random experiment are called Bernoulli trials if there are finite number of trials, trials are independent. Each trial has exactly two outcomes, success or failure. The probability of success remains the same in each trial. So, if all these four conditions are satisfied, then the trials are called Bernoulli trials. If we look at an example of tossing a coin 5 times, getting ahead being the success, then this is a case of Bernoulli trials. Rolling of a pair of dice 3 times, getting 7 as sum of numbers is a success, again a situation of Bernoulli trials. If we have 2 balls drawn in succession with replacement from a bag containing 4 white and 5 black balls, then getting white ball is a success, again an example of Bernoulli trials. What would not be a Bernoulli trial will be when I do not put the ball back before we draw out the second ball. So, if it is a without replacement situation, then such trials are not Bernoulli trials, because the trials will be not independent. So, you have to watch out for that, of course. Consider this example. A die is rolled 3 times. Consider getting a 6 to be success. So, S represents success, capital F represents the failure. Then the sample space now looks like success, 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 or SSF, SFS, FSS, etc. right? And therefore, if I take x to be the random variable representing the number of success, then again x can take the value 0, 1, 2 and 3. So, I have no success at all, or I have 1 success, 2 successes or 3 successes. Correspondingly, we can find the probability. If I know that the probability of success in this case, that is getting a 6 is 1 by 6. So, probability of success is 1 over 6, q the probability of failure, which is 1 minus p, is also 5 by 6. And therefore, with each of these values of the random variable, I can find the corresponding probability. Probability of x equal to 0, same as probability of FFF, same as probability of f into probability of f into probability of f, because the events are independent, right? And therefore, I get nothing but q into q into q, same as q to the power 3. If I am writing in terms of numbers, then it will be 5 by 6 to the power 3. Probability of x equal to 1 will be again getting 1 success. So, 1 success is followed or accompanied with 2 failures, and that can happen in 3 possible ways, and therefore, it will be 3 times of probability of failure into probability of failure into probability of success. If I am using p and q to represent the probability of success and failure, this reduces to same as 3q squared into p. Probability of x equal to 2 similarly will become 3 times of q into p to the power 2. Probability of x equal to 3 will become p to the power 3. Now, what is special about what we have calculated right now? If I put them in a table, that is the probability representation, probability distribution of the random variable, I have something like this. If you closely observe, there is something that you can see associated with the expansion of q plus p to the power 3. If I take the expansion of q plus p to the power 3, then the first term is same as what we have got as probability of x equal to 0. Second term is when you have probability of x equal to 1. The third term probability of x equal to 2, and the fourth term gives me the probability of x equal to 3. In general, I may say that if I take q plus p to the power 3 by binomial theorem that you learned last year, it's same as writing 3c0 q to the power 3 plus 3c1 q square p plus 3c2 q times p square plus 3c3 p to the power 3. Then each of these terms are representing the probability of a random variable. What is the pattern? The second term is representing the probability of x equal to 1. The third term is representing the probability of x equal to 2. So, if I want to generalize this altogether, I get something referred to as the binomial distribution, where the probability of R successes in n Bernoulli trials is given by the formula relation as probability of x equal to R to be same as NCR p to the power R q to the power n minus R. Remember that the R plus 1th term of the expansion q plus p to the power n will look like NCR p to the power R q to the power n minus R, and that is nothing but the probability of x equal to R. And therefore, in general, the binomial distribution takes the look of a table where each entry in the row p of x is actually coming from the corresponding expansion of q plus p to the power n, where we are now arranging or writing that expansion in the increasing powers of p. So, that is one precaution you must observe. Of course, p plus q to the power n is same as q plus p to the power n, but when we talk about it in relation to the probability of the success, then probability of x equal to R is NCR p to the power R successes. So, p gets multiplied R times into q to the power n minus R, the number of failures, right. Let us consider a problem and find the binomial distributions application in the same. The problem states that there are 5% defective items in a large bulk of items. What is the probability that a sample of 10 items will include not more than one defective item? So, in this case, we have x, very important to identify the random variable, to represent the number of defective items. Sample of 10 is a case of Bernoulli trials. So, when we talk about sample to be selected, it is always a case of with replacement. So, it is a case of Bernoulli trials, and therefore, x has a binomial distribution with n equal to 10, the number of trials, p the success, as I said there are 5% defective items. So, 5 over 100, so 1 by 20, and q the probability of failure will be 19 by 20. We want to find the probability not more than one defective, that means x must be less than or equal to 1. So, probability must of x equal to 0 or probability of x equal to 1 we are looking at, and therefore, by addition theorem probability of x less than equal to 1 is same as probability of x equal to 0 plus probability of x equal to 1. We did have a formula, probability of x equal to R is NCR p to the power R q to the power n minus R. So, I have all the possible values p, q, R and n. Substitute and calculate. In this case, obviously, you are not expected to simplify this beyond what we have here. Take something common if there is a common factor, and that would be your final answer. So, the probability that not more than one defective bulb is found will be 19 by 20 raised to the power 9 into 29 by 20. Another question would put things much more clear for all of you, and the problem states that in a hurdle race, a player has to cross 10 hurdles. The probability that he will clear each hurdle is 5 by 6. What is the probability that he will knock down fewer than 2 hurdles? Again, read the problem very carefully to understand what would be the random variable, and more importantly, what is a success. Clearing hurdle is not the success. In this context, knocking down the hurdle is our success. So, if I start by defining x to represent the number of hurdles knocked down, then x has a probability distribution, in this case I should say binomial distribution, with n equal to 10, q as 5 by 6, p as 1 by 6. We want to find probability that fewer than 2 hurdles are knocked down. So, x must be strictly less than 2. That means, x can take value 0 or 1. So, again with addition theorem in hand, probability of x equal to 0 plus probability of x equal to 1. Let us calculate using the formula. Probability of x equal to r is NCR p to the power r q to the power n minus r. It is only a calculation, are not expected to extend beyond what you see on screen. So, your final answer will be 5 to the power 10 upon 2 into 6 to the power 9. And so, the formula of probability of x equal to r, same as NCR p to the power r into q to the power n minus r, does come in handy to calculate the probabilities of cases as we illustrated just now. Also note that if you have a probability distribution where we are talking about Bernoulli trials, then a binomial distribution of such kind with n Bernoulli trials and probability of success in each trial denoted by p at times is also referred as b of n comma p. So, when you see an expression of the kind b of n comma p, then it means we are talking about a binomial distribution where there are n number of trials which are Bernoulli trials. That means, they are independent, finite, the probability of success does not change, right, and p represents the probability of success. So, if there are only 2 outcomes, success and failure, and other conditions being satisfied, then that is where we are looking at the concept of binomial distribution coming in use. With that, we come to an end of today's lesson. Hope you have learned something new and have found new confidence in this topic. All the best, and we will see you again sometime. Thank you.